Is the microphone? Okay. Good afternoon. I'm talking about maximal sharing in the Lambda Calculus with letrec. And the motivation of this work consists in the fact that increasing sharing in program is desirable in a number of situations. For instance, if one is interested in having code that is as compact as possible, so that that can lead to avoid duplication of reduction work at runtime. Also, another motivation of our work consisted in the fact that it would be useful to check a quality of unfolding semantics of programs. And this actually led us to two questions. The first question being how to maximize sharing in programs. And the second question, how to check in an efficient way for unfolding equivalence. And we look at these two questions, but we restrict them to an abstraction and the syntactical core of functional programming language, namely to the Lambda Calculus with letrec. And our results that we obtained are efficient methods for solving these two questions. Our methods consist basically of three steps. The first step is an interpretation of Lambda letrec terms into term graphs. Higher order ones first and then first order ones. The second step is basically the application of standard method, namely bisimularity and bisimulation collapse of term graphs and lambda term graphs that we will consider are an instantiation of those. And the third step is a readback operation that, given a term graph, it reads back a Lambda letrec term. We will see that these three methods in a second. We also have an implementation of these methods, and I will say something about complexity and extensions and applications of these methods. Our contribution is at first a conceptual one. We show how to reason about syntactically expressed sharing via an adequate term graph semantics. And the second conceptual part of our contribution would be to reduce problems about syntactically expressed sharing to problems that are accessible by standard methods. And our maximal sharing method extends the concept of maximal sharing that is known for first order terms to higher order terms. They are higher order terms with binding. Our method significantly extends the known optimization of common sub-expression elimination. We will see an example in a second. And it is targeted at maximizing sharing statically, and that means with respect to the unfolding semantics. And not at first, at least not a priori, not at first instance, to organize and maximize sharing dynamically during evaluation. And now let's start in earnest with a concrete example. Here you see a Lambda letrec term. Actually, it is a Lambda letrec formulation of a fixed point combinator, not a very efficient one, admittedly. But here is another Lambda letrec formulation of also a fixed point combinator. And now it turns out these two Lambda letrec terms have the same infinite unfolding, the same infinite term as their unfolding if one stepwise works out the let expressions and approximates an infinite term, then the term in the middle, the infinite lambda term in the middle is reached. So they have the same infinite unfolding. And now the question is how to get from the more involved Lambda letrec term to the easier. The method that we propose does the following. It interprets the Lambda letrec term as a term graph, then uses a standard method, namely bisimulation collapse, to compactify this term graph, and then from the compactified term graph read back the compactified Lambda letrec expression. The term that we obtain has the property that indeed it has the same unfolding as the original term, and its interpretation is the compactified term graph. The method actually consists of two steps. The first step is one that produces a higher order term graph. The next step is from a higher order, a first order term graph is obtained. This together forms our term graph interpretation. The second step, bisimulation collapse, we've already seen it. It leads to a bisimulation collapse also on the higher order object. The readback takes the compactified term graph and makes out of it the compactified Lambda letrec expression with the properties as seen. This is our maximal sharing method. And what about our method for deciding unfolding equivalence? We have already seen in this concrete example 2 lambda letrec terms that have the same infinite unfolding, and how would we go about to, in general, devise a method based on the steps that you've already seen to see that. Keep in mind, unfolding equivalence is something that involves an infinite term, and it's not easy to check, at least not a priori. What we do is interpret the one term by a term graph, the other one by a term graph, and then check whether these 2 term graphs are bisimilar. So in this case, we have reduced something that's not easily checkable to something that is checkable by standard methods. And also here the interpretation goes in 2 phases: higher order, first order term graphs. One term is translated, the other one, and then checked. And now let's look at these 3 steps a little bit more in detail. The interpretation. And here I slightly enrich the running example by one that's a little bit more interesting, because it can highlight the features of our method more better by a leading lambda abstraction and 2 more occurrences of variables. And now I show you how to translate this first, the simpler lambda letrec term, actually the result of the compactification, but because it's easier to demonstrate our translation. We built the syntax tree. You see here an abstraction lambda x, lambda f, and then f applied to r applied to x in a binding group which has the name R. This actually introduces a backlink in the syntax tree, which is indicated here in red, which is kept. Then I slightly deform this object in order to draw scopes, namely the areas in this syntax tree between lambda abstraction and occurrences of the variables in such way that the scopes are nested, as you see here. There are 2 scopes, one for lambda x and one for lambda f, which are properly nested. I indicate back bindings from variable occurrences back to the corresponding lambda abstractions. And now I make a term graph out of it. Out of an abstraction, I make a node that is called a lambda node, which has 1 successor. Out of an application, I make an application node, which has 2 successors, one for the function and one for the argument. And there is a third type of nodes, namely a 0 node, which indicates a variable occurrence. And that has back binding to the corresponding lambda abstraction. What we have obtained here is a higher order term graph. It's a first order term graph with an additional structure, and the additional structures are the scope sets. So this is the first part of our interpretation, namely a higher order term graph. And now this is actually adequate. However, it's not easy to compute with, and no standard methods are available for it, so it's better to get a first order term graph out of it that in a reasonable way encodes the scopes. How to do that? We actually use scope nodes, end of scope nodes, that signify the end of a scope for every edge that crosses the boundary of a scope. And such end of scope nodes get the back pointer to the corresponding abstraction. So now we are in a position to forget the scope nodes, and this is the end of our translation. It's a first order term graph, which we call a lambda term graph. It has some particular properties which you find in our paper. What about the more involved example? There, the syntax tree is a little bit more involved. Backbinding, deforming it, drawing scopes, making a term graph out of it with backlinks, having obtained a lambda higher order term graph, and then still going further, trying to encode the scopes into a first order term graph by using scope nodes and obtaining this graph. So actually now you see here next to each other the 2 lambda term graph interpretations of our running example. One corresponding to the original term that is more involved than the other, and now the next step would be to compare these 2. But first, properties of our interpretation. Our interpretation is actually defined formally by induction on the structure of the lambda letrec term. It is based on a similar analysis as that one of fully lazy lambda lifting, and it yields so-called eager scope lambda term graph. And by that we mean more or less minimal scope. And the crucial property of our interpretation is the following one, namely that two lambda letrec terms have the same infinite unfolding if and only if their term graph interpretations are bisimilar. And let's look at that in our example for the second step of our methods by simulation, check and collapse. Here you see again the two term graphs. And now in this case, it is the case that these two have the same, the terms from which we start have the same infinite unfolding as indicated earlier. So there should be a bisimulation between those. And what is a bisimulation? A bisimulation is a relation between the vertices of these two graphs that preserves the labels and that preserves the ordered successor relation and that relates the roots, as you see here. Relating the root actually gives an obligation which has to be met. It has to be met by creating an edge that relates the successor, which creates a new obligation which has to be met. Now we have an obligation to meet two vertices that are labeled with application symbols. That creates two new obligations, one for the left argument and another for the right argument. And we go so on a number of steps until here at the bottom we have an obligation between two variable occurrences, vertices, and that actually is met by an edge that is already there. So there is some cycling and loop checking in the bisimulation built in here. If I carry on further, then after a number of further steps, what we obtain is really a bisimulation between these two objects, indicated by this symbol. And actually what is the case is there is a functional bisimulation from the right term graph to the left term graph, indicated by this symbol. And actually the left term graph is the bisimulation collapse of the right one, meaning there is no term graph which is actually smaller than either of these two and that still would be bisimilar to both of them. The important property here is that the class of eager scope term graphs is closed under functional bisimilarity. And this means for our methods that the bisimulation collapse of the term graph interpretation of a lambda letrec term is again an eager scope lambda term graph. And this is crucial for our methods. About the third step, the readback, I will only say very little, namely what's the defining property of it. And the defining property of it is that if one is given an eager scope lambda term graph, then the readback should produce a lambda letrec term with a property that applying the interpretation you get out the graph from which it started. So the readback should be the right inverse of the interpretation modulo graph isomorphism. And how it is defined, the main idea is to construct the spanning tree of the lambda term graph and then use adequate local rules in a bottom-up traversal of the spanning tree to synthesize the readback. That's the idea of the readback. We have actually a tool implementing this on Hackage, and the tool is called Max Sharing, and it uses the Utrecht University attribute grammar system and also attribute grammar compiler, UUAGC, and you find examples and explanations concerning our tool in a report on arXiv that accompanies our paper. Console output of our tool is roughly the following. If you enter our running example in an easy syntax and you to our tool and you apply max sharing to a file containing this syntax, then first the lambda letrec term is pretty printed. Then a term graph, a proof is generated which actually corresponds to a finite states automaton which you see here on the right, and this is actually a finite state automaton representation of the term graph interpretation, which is then here state minimized into the DFA finite state automaton on the left, which corresponds to computing the bisimulation collapse in our case. And then this minimized automaton is read back, and the readback of this DFA is again computed and then pretty printed as a term as output of our tool. That is our tool. What about complexity? Concerning the maximal sharing method, it consists of three parts. So we should have a look at the complexity of these methods, of these parts. Interpretation turns out to be quadratic, both in the size, the time that is necessary for it, and in the size of the graph that is produced. Bisimulation collapse is possible in time m log m as state minimization of DFAs in our case, which here leads to a complexity of n quadrat log n in the size of the original lambda letrec term. The same holds for readback, which together gives us as a result that computing a maximally compact form of a lambda letrec term is possible in time n quadrat log n, where n is the size of the original term. What about unfolding equivalence? The first step is interpretation, is again quadratic, both in the time that is necessary and in the size of the graph that is produced. Checking bisimilarity is possible in almost linear time, namely m alpha of m, where m is the graph size, and alpha is the quasi-constant inverse Ackermann function, which in our situation here gives n quadrat alpha n. So this together yields the result that deciding whether two lambda letrec terms are unfolding equivalent requires almost quadratic time. In almost quadratic time in the size of the maximum of the two given terms. Okay, this was the complexity of our methods. What about possible extensions? So clearly we are interested in applying this method to full functional languages, but in order to approximate this, a first step would be for us to work on a core language with only constructors and case statements. And our ideas to deal with this situation would consist in the fact to model a core language for the functional programming languages at hand by enriching lambda letrec with function symbols that model constructors and case statements, and then adapt our methods in a very straightforward way to this extension of lambda letrec. Another thing to extend our method with is the following one, namely, it is known from common sub-expression elimination that too much sharing sometimes can be a bad thing. It can lead to space leaks, which are caused by disadvantageous sharing. And there are a number of remedies for common sub-expression eliminations done that are quite ad hoc. But one can also use a method for our situation, namely, first in an independent analysis, identify sharing unfit positions in a term that lead to sharing unfit positions, sharing unfit vertices in the term graph interpretation, and our idea to deal with it is to modify the term graph interpretation in order to constrain the bisimulation collapse to not introduce sharing at disadvantageous positions. Possible applications of our method would be to use maximal sharing repeatedly at runtime. Our method can be repeatedly used at runtime, and it is possible to implement our method directly on the supercombinator graphs, and this use of our method repeatedly during evaluation time could be coupled with garbage collection. Another possible application could consist in code improvement, namely to detect code duplication and provide some guidance for the programmer on how to obtain a more compact form. And the last application, possibly interesting, is function equivalence, namely unfolding equivalence clearly provides a partial solution for the undecidable function equivalence, and deciding unfolding equivalence may be relevant for proof assistance, for theorem provers, and for dependently typed programming language. And the last remark, because I forgot to say that the example that I showed to you, the collapse example I showed to you, was one that cannot be handled by common sub-expression elimination, that really shows what our method can do. But that is all, and thank you for your attention.
Questions? Oh, yes.
Thank you. Hi, I'm François Gauthier from INRIA. This reminds me of what I think might be a related problem. I'm thinking of the problem of deciding type equivalence. in system F with recursive types. So there you have the for all quantifier, which looks like your lambda, and you have the mu binder, which looks like your letrec. So this problem has been studied, and some efficient algorithms for it have been proposed. So I don't know if you're aware of that. Or
I have to admit that I'm not aware of the solutions to it, and at the moment I can't compare it directly to it. What I can say is it clearly is connected to many different situations to prove some, for instance, unfolding equivalence of recursive types. But this is basically a first-order question, and that has been shown with similar methods. So that's what you mentioned. Is for me more or less the first thing that these methods are applied in the higher order case. So it would very much interest me to learn more about that. But at the moment I can't compare it.
Thank you.
Thank you.
I'm interested in code structure that have explicit weakening, as you have used in your work. Have you tried to define the substitution or the sum of reduction directly on the first order term graph?
Yes, indeed. I've actually this is what I was busy with last time to define reduction directly on those graphs, and it's possible. I first tried to do it on term graphs, but I found it a little bit difficult, and I actually then used port graphs to implement reduction on these kind of graphs. But it is possible. And it also looks quite promising to me because there is this easy connection in our graphs between lambda terms and the supercombinator representations. One can go back and forth between that, and this I like very much. But thanks for your question. Yeah.
Any further question, remark?
Phil Wadler, University of Edinburgh. So this looks like a really nice general technique, and I was wondering if it subsumed the ideas in Kleene algebra. Right, in Kleene algebra, the hard thing is determining that A followed by BA star is the same as AB star followed by A, and that seems to follow automatically from what you're doing. So can you use what you're doing to subsume what they do in Kleene algebra?
Also here, I should say, I don't know, for instance, immediately the answer, but you mean that one would encode regular expressions by lambda terms and then use this method. I think this should be possible. I myself also have done work on regular expression equality, so I know the algorithms there, but I have not yet thought about translating these regular expressions into lambda terms. This is a good idea, it seems to me, but it had not occurred to me previously, I have to admit. But I guess so. If one has an efficient translation of which is perhaps linear or something like that from regular expressions into lambda terms, then clearly our method is applicable. Indeed.
So I think it might be worth looking at.
Yeah,
it'd be a nice connection, and also because the work on networking that we saw this morning, some of that work is applying Kleene algebra with tests in an interesting way. So if you can generalize that, that might have real practical implications for that other work.
Yeah, I thank you for this idea. This is really nice. Yeah, I have to think about it. I will do that. Thank you.
We thank Clemens again. We will convene in 18 minutes at 2:10. The speakers of the next session, please come forward to check your equipment. 10:03, of course.